Okay, so today we are going to see or learn how to find moment of inertia of different objects. In our previous class, we have already seen how to find moment of inertia of a circular ring. In today's class, we'll see a few other objects as well, like disk, sphere, or cylinder, and we'll see how to find the moment of inertia of that object along the main axis or along any one axis. And after that, once we have derived the expression for moment of inertia about one axis, then we'll use that expression and the perpendicular axis theorem or parallel axis theorem. We'll apply those two theorems, both of them or one of them, to find the moment of inertia of the same object about different axes. For example, let's start with the disk, right? A circular disk. What is the difference between a disk and a ring? Ring is just a wire. It has only length element or length dimension. I can say that this is the mass is distributed over a finite length, right? So it's not like it doesn't have any width. It has width, but if you consider width compared to length, width is very small, and that's why we neglect width and we move ahead only with length. That was ring. Now in disk, which is, say, it's actually like a plate, right? So it's a circular plate. It's a circular, you can say, something which has an area. Now again, it's not like it will have only area. It will have area as well as height, that is depth, right? Circular disk like this, it will have depth as well. So disk will be like this and it will have some depth, but the depth will be very less as compared to other dimension, that is the area, or you can say the length and the width. So here there is no length width, but the radius, if you consider this is the diameter, this is the diameter. So diameter and thickness, if you consider this, thickness is very less as compared to the diameter, and that's why in this case we'll consider only area, right? Okay, now how to find moment of inertia of such a disk? So to start with, we'll actually start with disk. Suppose that this disk is actually kept like this. Okay, suppose this is the circular disk. It is kept like this in the horizontal plane. The plane of the disk is in the horizontal plane. So it may look like this, just like we have drawn the diagram for so this is our disk, right? It has width, it has height, it has depth or height as well, but that depth or height is very less as compared to the diameters, right? So this plane surface, it has some area. Now to start with, we will go with the main axis of this disk, which is nothing but the axis which passes through the center and perpendicular to the plane. So this is the axis along which we are going to find out the moment of inertia. So that means we want it to rotate it like this. Okay, now what else? Suppose here this is our origin and this is our x-axis and this one is y-axis. So actually the disk is free to rotate along the y-axis. Now how to find the moment of inertia? So basic definition of moment of inertia is what? mr square, that is total mass into r square. So but in case of continuous objects, what we said, that we'll start with very small object. We take a very small object like this, right, of some thickness. Okay, suppose this small object or this small element, right, which is situated somewhere on the disk itself. So it's a portion of the disk, right? So we have to find moment of inertia of this. Now suppose the radius, this radius, that is from center O to the inner wall, let that be equal to x, right? So that is equals to x, and the thickness, this thickness, that is on this, suppose this ring is like this circular, and this is the radius, and we have taken a slice of this disc. So that slice of disc will be nothing but a ring, and it will have some thickness. Let us say that that thickness is dx, right? So this thickness of this ring is actually dx. So dx is the thickness of that circular part, or the disc, or that part of disc, that is the thickness, right? Okay, now in this case, if you open this small portion of the disc which we are discussing here, if you open this, you will see that it is nothing but a rectangular area like this, whose length is 2 pi x, right, and whose thickness is dx. So the thickness of this strip, which is actually a rectangular strip which we got by opening this, right, it will be a rectangular strip of thickness dx and length 2 pi x. So, and this entire radius is r, that is the complete radius of the disc, right? So now what is the area of the total disc? So total area of disc, this is equals to pi r square, right? Coming to the next part, if total mass of disc, let that be equal to m, right, and radius of the disc is anyways given here, r. So now in this case, what will be mass per unit area of the disc? It will be m divided by pi r square. Okay, so that is done. Now this small segment of the disc, that is this segment which is shown here as a smaller disc inside the bigger disc, if we consider that, there will, and we already said that that is actually an area. So in that case, what will be that will be a ring. So what will be the area of small ring element? We'll say that that is a ring element, this one. So what will be that? That will be nothing but the, as you can see, it's almost a rectangle. So it's circumference, that is length, that is circumference, into width, that is dx. So this will be equal to this small area, that is dA. This will be equal to the 2 pi x into dx. Is that clear? So this is 2 pi x into dx, that is actually your small area element. Now what will be the mass of this small element, this ring? So the mass will be equal to the mass per unit area, that is m divided by pi r square into the area, and area is what? dA, that is 2 pi x dx. So this pi and pi gets cancelled. So you have 2m divided by r square x dx. This is the mass of this small element, right? Now if we have to find the total, moment of inertia, right? So first we'll have to find the moment of inertia, that is di, for this small segment or this small element. So first we'll find moment of inertia of this circular ring which is inside the disc about the same axis, right? So about the ring, I think we already know that in the ring, about main axis, what is the what is the total, what is the moment of inertia for the ring. So for ring, we know that this moment of inertia is equal to total mass into r square. This we have derived in the previous class, right? So same thing I am going to write here. Only thing is this mass and all, mass and radius will be different here. So di, that is the moment of inertia for only this segment. So this will be equal to the mass which we have found out here into x square, which is actually the radius of this. So m into r square, where r is the radius of the ring. Here the ring's radius is only x. So that is actually di, that is mx square. So what does it show? That if x will change, mass will change, and even the di will also change, right? So now if I have to find the total moment of inertia, then I'll have to integrate it. But before that, as you can see here, mass is also variable, x is also variable, and there are two variables. So now try to write them in terms of only one variable, because then only we will be able to integrate, right? We know integration right now, we know integration only in terms of one variable. So this is the mass. Mass is actually in terms of x. So if I'll substitute here, I'll get this di in terms of only x, right? And all others will be constant, only x will be the variable. So just write mass value here, that is expression for mass, that is 2m divided by r square into x dx. So this will become x cube dx, right? So 2m divided by r square into x cube dx, that is what di is. Now what do we have to find? Total moment of inertia. So total moment of inertia will be what? It will be integration of di. So integration of di. But what is di? Di is this. Now in this 2m divided by r square is anyways constant. So I'll keep this outside, and x cube dx. Now x varies, right? In this disk, you see that x will start from here. I mean, this disk is actually made up of small rings whose radius, if it is the centermost, it will be 0. Then you keep on increasing, x will keep on increasing, and ultimately its maximum value will be r. So x will vary from x is equals to, here we write the limits of x, that is x equals to 0. Generally we don't write x equals to 0, but if you write, it is not wrong. It is just to make it clear that here it is x which is varying, and that's why these are the limits of x. So x is varying from 0 to r. So even if you don't write x equals to, then also it means that it is x which is varying from 0 to r. Now you just have to integrate this, and integration of x cube will be what? X to the power 4 divided by 4. So this is equal to 2m divided by r square into x to the power 4 divided by 4, and the limits 0 and r. So now what do you have to do? Substitute substitute r in place of x. So this will be 2m divided by r square into r to the power 4 by 4 minus 0. So this will be total 2m divided by r square into simply r to the power 4 by 4. R square cancels this, and this is r square. So ultimately what you will get, that this moment of inertia in case of ring about the main axis, in case of disk about the main axis, is 1 by 2 mr square. This is the moment of inertia of disk about the main axis. So we have found only about the main axis till now. Now we have to find same moment of inertia, moment of inertia of the same object, but about different axes. So now we'll change the axis and we'll see how to find the moment of inertia for different or about different axes, right? So what will we do now? Now we'll have to apply other theorems. Just like we have seen in case of ring, we will do the same thing. You already have the moment of inertia of this disk about the main axis, right? Now you have to find the moment of inertia about say an axis which is almost which is actually the diameter. So that means what? You have a disk like this, right? Okay, what do you have to find? You have to find along the diameter. So first, what do we know? We know the moment of inertia along this axis. So along this axis, moment of inertia I is actually equal to what? This is equal to, just now we have found, that is half mr square. What do you have to do now? Now you have to find the moment of inertia along the diameters. So diameters means what? Diameter will be actually in the plane. So this is a diameter, right? Same way, this is a diameter. So there are many diameters which you can draw, but we have drawn two diameters in the plane of the disk which are perpendicular to each other. So these two diameters are perpendicular to each other, right? Okay, why perpendicular to each other? Because now we have a theorem, right? The perpendicular axis theorem. What does that theorem say? If you have moment of inertia along this, then moment of inertia along, so two axes which are perpendicular to each other. If you know moment of inertia along say these two perpendicular axes, that is Ix and Iy, then you can find Iz is as well, and that Iz will be equals to Ix plus Iy. That is the perpendicular axis theorem. Now by symmetry we can say that if I choose any diameter of this disk, the moment of inertia will be same. That means suppose this is ID, that is moment of inertia along a diameter, and this will be also ID, and these two are perpendicular, and this Iy which we have already seen in the previous section, that this was the y-axis, and along y-axis we have already found that it is 1 by 2 mr square. That is along the main axis of the disk, and that main axis is the axis which is passing through the center and is perpendicular to the plane of the disk. So that means what? As per this theorem, Iy should be equals to Id plus Id, because Id and Id, these two axes are perpendicular to each other, and the third axis Iy is actually perpendicular to both these axes. So that means what? Iy, or I can say 2 into Id is equals to Iy, or Id will be equals to Iy divided by 2. Iy is mr square by 2, so this will be equals to mr square by 4. This is the moment of inertia along the diameter of the disk. Now if you observe these two things, means this and the ring we have already seen earlier. In the ring, the main axis, if we took, the moment of inertia was mr square, and in the disk, along the same axis, it is 1 by 2 mr square, right? And same thing with the moment of inertia along diameter as well. So we have already found now the moment of inertia along the diameter. Now what do we have to find? Now suppose we take another case, that is we know moment of inertia along the diameter. So suppose this is the diameter, we know this moment of inertia. What if I want to find out moment of inertia along a tangent? And obviously tangent, if I want to find the tangent, if there is a tangent along which I want to find the moment of inertia, suppose this is the disk, and I want to find moment of inertia along this tangent, right, in the plane of the disk itself. So tangent can be like this as well. If this ring, as you can see here, ring is in the plane of board, but I can draw a tangent like this as well, or at the same point the tangent can be like this. If you observe this tangent is actually perpendicular to the plane of the disk. There can be other tangents as well. So if the disk is like this, suppose this is the surface of the, this is the edge of the disk, then tangent can be like this, tangent can be like this, tangent can be like this, tangent can be like this as well. We are talking about this tangent, the tangent which is in the plane of disk. So this is that tangent, right? There can be other tangents as well. Now, along this tangent, suppose I have to find this moment of inertia. That means if it rotates around this, then what will be the moment of inertia? Let us say that this is IT. Now how to find that? What all we know? We actually know this moment of inertia, that is about the center. We know moment of inertia along this diameter, or along the diameter, we know. So what we do is, we actually consider the axis along the diameter, because we already know the diameter, I mean the moment of inertia here. So moment of inertia along the diameter we know, and diameter is a line which passes through the center of disk. That means it actually passes through the center of mass of the disk, right? So the reason behind this is we want to apply the parallel axis theorem. So if this is the center of mass, if this is the distance between the axis along which you want to find the moment of inertia and the axis which passes through the center of mass. So there are two axes here, one axis which passes through C, that C is actually center of mass, and we have to find moment of inertia along this new axis here, which is on the left. And as you can see here, on the left, whatever axis is there, that is actually parallel to the axis which is passing through the center of mass, and the distance between these two is D. Then we know that in this case, suppose if this is say P, so moment of inertia along the parallel axis is equal to moment of inertia about the center of mass plus the total mass of the object into d square. This is our parallel axis theorem, and we are going to apply the same theorem here. We have to find t here. Now what is the distance between these two axes? That is r. So these two axes are parallel to each other. We know the moment of inertia along diameter, that is mr square by 4. So what will be the moment of inertia along the tangent? From here, what can we say? Along the tangent, this will be equal to the moment of inertia along the center of mass. So center mass is d. Now, not along the center mass, along the axis which passes through the, or about the axis which passes through the center mass. This axis also passes through center of mass, right? But we are not considering this because our axis should be in, if we want to apply this parallel axis theorem, these two axes should be parallel. So IT, so I am considering the diameter. So IT will be equals to ID plus m d square. Here what is d? D is r. So this will be nothing but 1 by 4 mr square plus mr square, which is nothing but 5 by 4 mr square. This is the moment of inertia along the tangent in the plane of the disk, that is 5 by 4 mr square. Now we can also or be asked to find the moment of inertia of the same disk, but this time and about the tangent, but this time if you see, the tangent is perpendicular to the plane. It is like this. If this is your circular disk, tangent is here. So this is perpendicular to the plane of the disk. So this is that tangent, right? So let us say that moment of inertia along this is also it, but it dash, that is another tangent. Okay, obviously in this case I won't take the diameter, I won't take the moment of inertia along the diameter. What will I take? I'll take that moment, I'll take actually the moment of inertia along the main axis. This is the axis or the main axis, that is this axis is also perpendicular to the plane of the disk. So here what is this moment of inertia? This is actually Iy. Now if I have to, similarly if I have to find it dash here, what will be that? That will be nothing but Iy plus mr square, just like we have done earlier. And what is Iy in case of disk? It is half mr square and plus mr square. So the total will be 3/2 mr square, right? Okay, now the same question can also be done in a different way, even that is possible. How to do that? Suppose this line, if you consider, this is nothing but the diameter, this is the diameter, and what is this? If I consider diameter here, I mean an axis here, so that axis will be actually parallel, or that tangent will be actually parallel to the plane of the disk. So one axis is like this, which is parallel to the plane of the disk. Another axis is also is actually the diameter. So and diameter is also in the plane, but this diameter and this tangent will be actually what? Perpendicular to each other. And this tangent, which is actually perpendicular to the plane of the disk, will be perpendicular to both those axes. That is, suppose it is like this, there is a tangent in the plane. So there is a tangent in the plane and I am considering this diameter. So even this is possible, right? This is ID and this is IT. The tangent, this tangent is actually perpendicular to the plane of the, this is perpendicular to the plane of the disk. So it will be something like this. And now this tangent or this axis will be perpendicular to both IT and ID. I mean the tangent in this plane and the diameter. And here I can apply the perpendicular axis theorem, right? So till here we have understood. We have got the main body. We have found the inertia about the main body axis. Then we have used the perpendicular axis theorem to find the moment of inertia along the diameter. Then we have used the parallel axis theorem to find the moment of inertia about the diameter, about the tangent, which is in the plane. We have used parallel axis theorem to find the moment of inertia of this tangent or moment of inertia of this disk are about the tangent or about the tangent which is perpendicular to the plane. Now we are finding the moment of inertia about the same axis but using a different theorem. So even that is possible. So this was tangent in the plane, this is diameter in the plane, tangent, diameter perpendicular to each other, and this is the tangent which is actually perpendicular to the plane of the disk, and I have to find moment of inertia along this or about this tangent. So I just have to apply the perpendicular axis theorem. So what will be that? Again, IT dash will be equals to sum of these two, that is ID plus IT, right? And what is ID? ID is mr square by 4 And what is IT? IT is this, that is IT is 5 by 4 mr square, so 5 mr square by 4. If you add them, total will be 6 mr square by 4. If you simplify, you will get the same, that is 3 by 2 mr square, right? So this is how, I mean, this I did just to show you that in some cases, by applying both of these theorems, you will be able to get the result, whether you apply the parallel axis theorem or whether you apply the perpendicular axis theorem. In both the cases, you will get the same result. So moment of inertia about any axis you choose remains constant or remains same, irrespective of the choice of theorem you use to derive that expression. So here we have got about how many axes? About the main axis, about the diameter, about the tangent in the plane, and about the tangent which is perpendicular to the plane, right? So that's all about the disk. Now we'll see some other shapes as well, and the derivation will be similar, it won't be different. The similar approach will be there. First you find the moment of inertia along the or about the main axis. Using, you may have to apply the integration, apply the integration, and after you got that, then what you have to do is you have to apply either perpendicular axis theorem or parallel axis theorem to find moment of inertia along different axes, right? Okay.